Today, let's go beyond the perturbation theory limit and look at a phenomenon known as high harmonic generation, which was the subject of the 2023 Nobel Prize in Physics awarded to Pierre Agostini, Ferenc, Krausz, and Nonlinear. When we started our discussion of spectroscopy, classical spectroscopy uses weak light sources. The Beer-Lambert law holds everything is in what we call the linear regime, right? The electromagnetic field of light doesn't change the characteristics of the system that we're probing. We have transitions between real states, and the response of the signal to the excitation intensity is linear, right? So for example, in photoemission, we have one photon in, we get one photoelectron out, as long as the photon energy is above the work function. Then lasers were developed. And not only did that allow us to get beams that we could very directionally propagate and focus down into tight spaces, but it also meant that we could make pulsed sources with short pulses down in the nanosecond regime, which made accessible much higher field strengths. And these field strengths, much higher field strengths, brought us to the nonlinear regime. The laser is creating virtual states of the molecule laser field system that only exist when the laser is interacting with the molecule. And because of this, we get a nonlinear response of this signal to intensity. So in processes like laser-induced fluorescence or resonance-enhanced multiphoton ionization, the signal goes up as the intensity is increased by a power n greater than 1. This is also known as the perturbative regime, right? The field strength of the electromagnetic field, the laser field, is still small compared to the field in the atoms and molecules, and so we can use perturbation theory to describe what's going on. For instance, we can think of the polarization that's imprinted upon our atomic or molecular system and expand that in terms of the nonlinear susceptibility with increasingly high order terms in the electric field strength. But we kept developing lasers. We got to shorter pulses. We could make picosecond pulses, which allowed us to look at vibrations in real time, how atoms were moving. And as pulses went sub-picosecond and into the femtosecond regime, that allowed us to probe reaction dynamics in real time to see products of reactions formed in real time after laser excitation. But of course, we weren't satisfied with that. We kept going to higher power sources with shorter pulses that we could focus down, and this finally brings us to the high field physics regime, where the laser field is now appreciable compared to the potential, the electric field strength that is holding electrons in the nucleus. And with new physics come new phenomena. So we can look at our old toy models of atoms and probe those in more detail. And we can look at, for instance, those quantum jumps, quantum leaps between states, and say, just how fast is one of these quantum leaps? So let's take a look at this phenomenon known as high harmonic generation and how we can use it to generate attosecond pulses. So we'll start off with our Ti-sapphire laser, and we're going to build that into a system where we get a molecular atomic beam, and we're going to pass our light through that beam that's coming through the tubes here. The light propagates through, interacts with the atoms in the system, and then light comes out the other side. Those are the high harmonics. Let's look at how that's generated. We're going to introduce here a simple semi-classical three-step model to describe what's going on. So we'll start off with the laser field. It has an oscillating electric field. And then we'll put an atom in this. Of course, at the nodes, there's no electric field strength, and so there is a potential, the atomic potential, that's holding an electron inside of that potential well. But as the field strength of the laser increases, this is going to perturb strongly the atomic potential that's holding the electron in. It's going to pull down this barrier that's holding the electron in, allowing the electron to tunnel out of the system. Now, once tunneling occurs, the electrons pretty much have zero kinetic energy, but those electrons are going to get accelerated. Most of them get accelerated away and are lost to photoionization, but some decide to return to the atom and the atomic potential after they have gained energy through this acceleration as the field strength changes. And once they return to the atomic potential, they got to release that energy. And when they release it in the form of photons, the high harmonics. And what we see is something very interesting in the spectrum of light that comes out of the system. We get very sharp peaks at the well-defined energies, odd harmonics of the fundamental wavelength, the fundamental photon that was driving all of this. Why? Because this acceleration that occurred for the electron is taking energy out of the laser field, and it does that in quanta of the laser field in terms of the energy associated with this wavelength of light that was used to drive the process. Furthermore, not only do we get a bunch of peaks, we get a bunch of peaks that are all out there in a plateau. They're all at similar intensities. Furthermore, this light is coherent. It has a well-defined phase relationship. And if we've got broad energy band of coherent light, the energy-time uncertainty relationship tells us that we should be able to change that broad energy spectrum transform it into pulses that have a very short duration. And indeed we can. So if we return to photoemission and now think about our few cycle attosecond pulses coming in and interacting with an atom, let's look at the photoelectrons that come off. And we can ask the question, just how fast was that transition? But first, of course, we're going to need to be able to produce a train of attosecond pulses. And this was demonstrated in Agostini's group back in 2001, which allowed the development of techniques that could allow us to address the question, how fast is instantaneous? And the first groundbreaking experiments from Krausz's and Lulier's group that looked at photoionization soon followed. And they looked at two rare gas systems, neon and argon. It took a lot of further work to really sort out the details of what was going on, but we figured out that the ionization process is quite complex. It begins right at the beginning of the pulse, but as the pulse interacts with the atomic system, a phase shift is introduced into the wave packet that describes the electron as it transitions from being bound in the atom to being a photoelectron. And that phase shift is equivalent to a delay that depends on whether one or two photons are involved in the process, and whether it's a one or two electron ionization process. A one electron process is simple ionization. A two electron process is, for instance, a shake-up process. The one electron process is faster. The electron kinetic energy is also important. As you change the excitation energy, more energy is left over for electron kinetic energy. The delay is largest at threshold, and as the electron kinetic energy increases, the delay decreases. There are other subtle effects introduced by the angular momentum change and the angle of photoemission. But in both systems, it was found that the p electron is removed more slowly than the s electron. For excitation at 105 eV in neon, that delay was about 11 plus or minus 7 attoseconds. The argon system is a little more complex. Again, the p electron is slower. However, it's a little more difficult to unambiguously measure that atomic response time because of the contribution of this tau cc term that is introduced by the second photon in the measurement process. What we see from these experiments are that atomic and molecular systems begin to respond immediately to electromagnetic excitation. However, the wave packet dynamics that represent the transition from one state to another, these dynamics evolve over an attosecond timescale, and this attosecond timescale can be probed directly by experiments.